Right, guys. Hello, and sorry for this unexpected online lecture. I know we are all slightly sick from them from 2020, 2021. I don't know if you studied in 2020, so maybe you're not as sick of them as as I am. But sorry about that. But just 1 week for everyone's safety. So this lecture, we're going to discuss something quite interesting. So I hope, 1 second, it's just one. So I hope it will be, worth your time coming. In fact, we're going to discuss the concept of stability. So the concept of stability is a key idea in control theory. It is both a complete foundation of our course and more or less complete foundation of the whole engineering field of control theory. Stability is the main criteria of success or failure, is the main goal when designing the system, is the main way to assess the quality of the system. So in a sense, it is everything for us. And also not very difficult to understand either. So let's just go into it and we'll see what stability is. All right, here is slides as we go along. I'll just skip that. All right. First, before we can discuss stability, what we need to try to understand is the idea of a critical point. What is a critical point? Well, let me try to use the fact we are online to the good of our presentation. So consider this ODE. Like this is just the ordinary differential equation, same as we saw yesterday, right? So assume you can find such a value of x here, like let's say we call it x naught, that this function turns into 0. So this function here becomes 0. That means that the state of the system is no longer going to change. So as soon as you found such a value of x, that this is true, this value is not going to change. So the solution for this equation, will become a constant. It's not going to change with respect to time. That state is called the critical point or a node. Is it clear what we're trying to see here? So like, for example, imagine if you have a system and the number 2 is such a critical node. It means that the solution is going to be just a line with respect to time.
It will be a line forever, or like in a parabola when there is also a critical point in the bottom.
Yeah, that is the interesting question, right? For parabola, what you have is like what we call a critical point is just wherein the derivative is equal to 0. But second derivative of the parabola is not equal to 0. So the derivative will change with time, and hence, the function will grow back. Here, you don't have any second derivatives. The derivative is going to be equal to 0 as long as x is equal to 0. Oh, sorry, as long as x is equal to x naught, derivative is going to equal to 0. But as long as derivative equal to 0, x is not going to change. So yes, it is going to be forever in both directions too. That is an interesting argument that I'm not going to go through today, but it's very easy to prove, right? If the solution is extended in one direction as a constant, it has to be extended in the other direction. Right? Is something to think about. All right.
Okay, thanks.
No problem. So this is the idea of a critical point, a state which turns your right-hand side to 0, and hence your rate of change of your state is 0, and solution is constant. That is the whole idea. Sounds like, something profound when you call it a node or whatever, but it's not. It's just a equation becomes like, instead of a differential equation, becomes basically algebraic equation with a constant solution. That's all. Okay. All right. So now we can discuss the idea of a stability of a node. So by definition, we call a node stable if and only if for any sorry, for any constant delta, there exists epsilon such that I mean, I guess you can reverse it, but let me try it first this way and then we'll reverse it. So for any constant delta, there exists epsilon such that x in the initial moment, like initial condition x, being in the vicinity, delta vicinity of x naught, this implies that the solution at any point of time is going to be in epsilon vicinity of x naught. So let me just demonstrate it. So imagine your solution looks like this. Okay. And imagine this is x naught. So this here is delta vicinity. And here is epsilon vicinity. So what you want basically is that if your pick an x in this vicinity of x naught, it would imply that the solution is going to be bound by some vicinity epsilon. You can write it the opposite way. You can say x naught is stable if I wonder, like for linear systems, you can definitely try to say that, right? You can say that for any vicinity epsilon, you can find such delta that the solution is going to stay within the vicinity. All right, I'll drop this discussion here, but just want to point out that this, exchange between epsilon and delta is, is something that is worth your time thinking about. Yes, please.
Epsilon should be less than delta.
No, the relations are irrelevant. Epsilon should actually be bigger than delta always. Like the way I've drawn it here is, I think, slightly misleading. So let me just draw it like this. The reason is actually has to be bigger. It's very simple because initial condition 0 is also a t, right? So this like x of 0 minus x naught by norm should be less than or equal to epsilon as well, because you can substitute here 0. So they are always, epsilon is always better, bigger than delta. at least the way I understand this implication. By the way, this whole thing is not by any means how should I put a foundation. Like this whole discussion is not the foundation of our further derivations. That's why I'm so lackluster about what is correct, what's not correct. That is more to give you like a language. And since you're familiar with epsilon delta notations in limits, calculus, differential equations, etc., I thought I would put it for you in this form. But we just need to understand the concept of stability. The particular language in which you describe it, epsilon delta or something else, doesn't really matter. Like you can pick it up in a textbook or write it on your own. So, don't worry about it too much. But do think about it. This implication is interesting. Like, does what delta implies epsilon? Like delta vicinity implies epsilon vicinity? Is it like the only way to represent stability? Maybe not. Simply, think about it after the lecture. Try to see if there is some details to it. Can you, for example, write it the other way around? All right, that's just thought experiments. So the more easy way to think about it is to say for any initial point that lies at most delta away from x naught, the rest of the trajectory is going to be at most epsilon away from x naught. So the trajectory is not going to go further than epsilon from the initial, so from the node. All right, so that's the definition. And less precise, but I think more useful, you can think of it this way. The solutions with different initial conditions do not diverge from the node. You understand the concept of divergence, right? Let me try to maybe clean everything. You understand the concept of divergence, right? The concept of divergence, I think, if I have to guess, you think about it this way. Like here is something that converges, and here is something that diverges. Does it look close enough to how you imagine divergence? Here is another example of divergence. Does it look like divergence to you, or is it something else that you imagine when you hear the word?
Yeah, it's familiar.
I agree, Vyacheslav Sini.
Excuse me, sir, before we move on, you stated that a critical state, a critical point.
Your sound is terrible. Please stop.
There is a slight problem with your mic input. If you want, you can type your question in the chat. I'm sorry, or if you want, you can try to lower your volume. We'll probably be able to hear it. This is just slight, disturbance with your mic. All right. While we, wait for the question, I will just continue. All right. So you can imagine this. You can imagine this whole thing as this, right? As the solution does not diverge. That's basically what it says. It doesn't say it converges. It says it simply doesn't diverge. So it doesn't go away. So as long as you pick this type of initial conditions for some delta, it doesn't diverge. That's the idea. Basically, here I don't say that you are limited in your choice of delta this way. I'm only saying that for some delta it will be bounded by some epsilon, for different delta it will be bounded by different epsilon. But I don't say that you cannot choose a very big delta. You can. That would be discussions that we can have later about the size of the deltas. Question in the chat. You stated a critical point is a state that does not change with time, right? Yes. Critical point is a state which itself does not change with time. So let me just one more drawing. Let's say that is x naught. The solution that starts directly from x naught is going to stay at x naught. But solutions in the initial vicinity can, for example, do something like this. They change. X naught itself does not change. Correct. Okay, sorry for taking a while to say such a simple thing as is written here, but it is important. So you'll see it in a bit, just how important this whole thing is. All right, now we can also introduce the concept of asymptotic stability. Something is asymptotically stable if it converges to x naught. Let me put it more precisely. For any initial condition that is at most delta away from x naught, the solution in the limit converges to x naught. Just one more time. Sorry for, I want to answer the question in the chat because we can, we can diverge in our discussion. So let's first answer all of them. What is the difference between does not converge, does not diverge, and converges? Does not diverge is sine wave. Sine wave does not diverge from anything. Oh, sorry, I probably should draw something more parallel. So sine wave does not diverge from horizontal line, right? And what do you mean converge? Well, I can say will be a good example. Like a solution of a differential equation converges. Like, for example, x equals to e minus t converges. We can add like sine t if you want. This converges, and this does not diverge. This is x equal to sine t. Does it clarify the idea? Yeah, great. There was actually the same answer in the chat. Great. Okay, good. So the difference when we say limit, maybe okay. So just for everyone and for Artyom specifically, after the lecture, just review your series by calculus, your series, your limits, and the concept of convergence. Since limits has nothing to do with what we are, I'm using limits here, right? But I don't like that's all that I'm using them for. The concept of convergence and the concept of a limit are slightly different, and I don't want to discuss it here. So just please review it. Concept of convergence is best discussed in the context of series, and is good practice to just review the terminology. All right. Sorry for everyone who feel like we are dragging, but we have to be very clear about those concepts. All right. So asymptotically stable means that for any initial condition in the vicinity of x naught, delta vicinity of x naught, the solution converges to x0. So as time goes to infinity, the solution approaches x naught. And that's it. And approaches it asymptotically, as we say. What do you mean by asymptotically, by the way? That is maybe something that you haven't seen too often. Let me see if I can create a blank slide. 1 second. All right. Can you see the whiteboard? You probably can. Let me know if only I can see it. So you can have this let's say x naught here. And the solution can asymptotically, or can approach it. Let's say here is a solution. I will even take a different color for clarity. Here is a solution that approaches it. It approaches it as in the sense that it gets closer. The more time passes, the closer it gets. But let's say the solution x equal to x of t in the limit as t goes to infinity. Let's say the solution approaches some value, let's say 3, and let's say x naught is equal to 2. That is possible, right? You can imagine the solution slowly going to, and the solution is always bigger than 3, for example. So it slowly decreases, so it slowly gets closer and closer to 2, but it's never going to come close enough to the value 2, right? It's always going to approach the value 3. So even though it gets closer, it's not actually converging. It just doesn't diverge. Doesn't converge, sorry, asymptotically. All right. That's the idea. All right. Go back. Okay. So this is the idea of asymptotically being asymptotically stable. It means that you asymptotically the solution asymptotically approach x naught. So not just that it doesn't diverge, not just that it kind of gets closer, but that at infinity, at time as time goes towards infinity, it gets exactly towards x0. All right. So I hope this is clear. We can say this whole thing as all solutions with different initial conditions converge to the node. That is how we can shortly designate this whole problem. Okay. Now, a few examples. Of stability and stable nodes and unstable nodes. So let's consider this system. First example. So this system, and let's say it has a solution x equal to 7. X equal to 7 is indeed a solution. Actually, every single x is a solution of the system. Every single x is a node, critical point. Okay, the solution is stable because any other initial condition other than x equal to 7 will produce a solution that does not diverge. But they don't converge either. So it is stable, but not asymptotically stable. And, you know, it is a way to think about it in terms of those definitions, but just think about the system. What it does is it takes initial condition and doesn't change it. So yeah, it is stable. Nothing diverges there, but it is not asymptotically stable. All right, then you have the system. And let's say solution x equal to 0. That is the only solution of this equation, right? Sorry. This is not. This is only a stable critical point or node of the system. I don't think it has any other nodes, right? So if you plug this here, you'll get a, like, it becomes a solution. So this is a node. And this solution is stable and asymptotically stable. Why? Because any solution of the system will tend towards 0. How do I know? Well, let me write it. I'll get to the whiteboard again. So how do I know? Well, let's consider the system one more time. X dot equals to minus x. What is the solution of the system? Well, the way we think about those systems is this. We say it is dx dt equals to minus x. Then we bring this guy at dt to the right hand side, and we bring x to the left hand side. So this is how it is written. Then you integrate both sides. Let me write it here, please. What is the integral of dx divided by x?
Natural logarithm.
Yes. It's a natural logarithm. So you have logarithm x equals to, here is integral is minus t plus a constant. Okay, good. Now, what do we do next? Next, we say that x is equal to e to the power minus t plus c, right? Well, we can actually open those things, right, using its power. Because there's a power, we get this. But this is just a constant, right? Hence, this is just a constant, like a power to the unknown constant is just an unknown constant. So we can rewrite it as such. And that is a solution. Oops. It's a little bit difficult with what they call it, with the drawing pad here. So apologies for lines going every which way. This is a solution. It's hopefully familiar to you. This is a constant that you can identify based on initial conditions. But whatever the constant is, it doesn't matter, because the convergence is defined by this thing here. And you can see it is always negative, because time is going, like, if we consider time being, you know, positive, but it doesn't matter, like, you know, even if time was negative, it's basically, it's as time goes forward, this coefficient goes towards negativity. So it's going to become, you know, more and more and more negative. And that means that the solution is going to converge towards 0, because this approaches 0 as t approaches infinity. So I hope this makes sense. Now, does it make sense to discuss what this approaches as time as t approaches minus infinity, for example? So let me just write it. That is probably not something you necessarily need in this discussion, but we'll actually use it, I think, next week. So let me write it here. So if you write it like this, that makes sense. It is 0 for any S node. Okay. On the other hand, if you were to write it like this, towards the minus infinity, this, you know, it becomes meaningless. Like it doesn't exist. Not defined. You can say that it approaches infinity, like, but which infinity? Minus infinity, plus infinity, depends on the sign here. And in general, like if it was oscillatory, if there was a sign here, it would become even more messy. So basically what I'm trying to say is we can look at this very simple equation and discuss how it evolves forward, but not backwards. And that will become a part, like a small, tiny part of our next lecture. It will just explain one small piece of mathematics that we'll encounter there. So you can keep it in mind if you want. All right. I think last time you requested that we have a break. It's probably a good time to have the break. We'll make it, let's say, 10 minutes. 10 minutes is not too long, right? Hopefully. You're not going to go all the way and not come back, right? So we'll have a 10-minute break. And after that, we'll see the criteria of stability. So is still extremely important. We saw definitions and what they mean. Now we'll see criteria after the break. All right, 10 by my clock, we'll meet back. we'll begin in 1 minute, right?
One, two, three. Is my sound better now?
Come again? Oh, sorry.
Is my sound better now?
Yes, your sound is perfect.
Great.
Excuse me, you said that the lecture is going to be online, but do you have any information about tutorial?
Tutorial will also be online for the same reason.
Okay, thank you.
Mhm. All right, we'll start back. By the way, let me know after the lecture if 10-minute breaks are a little bit too much. Though probably online lectures don't count the same as offline ones, right? So next week we'll see the, you know, what kind of breaks we want when we are in class. Okay. So this was it for the ideas of you know, what the solution of x equals to minus x is. By the way, we probably, let me go back to the original slides. We probably have one more example, and that is x dot equals to x. And you can see exactly now what the solution to this guy will be like. Let me put this notation somewhere. The solution to this guy will be something like x equals to e times t times s0, and that solution diverges because it will basically look like this, the solution. Or depending on the sign of C naught, it can also look like this. It can look like this, like this, like this, and so on. So you see, this is unstable, not stable, not asymptotically stable. Every solution diverges. Okay, so that is what we have. Now, hopefully we understand what stable means. But the task now is to try to see how we can determine stability. It was nice to solve equation by hand, but most equations, you know, it's not so easy to solve them, right? And you don't want to solve equations every time you want to analyze stability, because we will have to analyze it all the time. So now we'll try to work towards criteria. First, let's consider this expression here. This expression is a ordinary differential equation with external input. This external input here, we will discuss it later in the class, but I just wanted to write it here so you would see it for the first time. But this is going to be something we use all the time, right? This form with external input. We call it linear time invariant system, or LTI. Why LTI? Because nothing except better way to put it would be like this, because A and B are constant matrices. They don't change with time. That would be the way to describe it, why it is the linear time invariant. Right, but so far this probably looks strange to you. Like, what is this input? So we'll drop it for now, and we'll go back to something that is extremely familiar. X dot equals to AX. That is what you practiced last time during practical session. That is also what you saw on the lecture. We were trying to write everything in this form, right? So any linear differential equation, we try to write it in this form. This is called autonomous system. Now, it is still LTI because A is still time invariant, like it doesn't depend on time, A. But it is also autonomous because it doesn't have any inputs. Like it only depends on the state. The state of the system defines its behavior completely. That's why we call it autonomous. It is autonomous from any external inputs. And that is, I think, pretty much the systems that you studied in your differential equations course. Let me quickly see the chat. So is U dependent on time or constant? U can be anything, but again, I will avoid discussing U right now. And U can be dependent on time, can be dependent on state, can be a lot of things. Is input. All right, is input U a function of time? Yeah. So as I said, I just pointed out here because we'll have to go back to it. So I want you to have this, memory that something like this exists. So next time you see it, you become, that's interesting. That's what we want to learn. But let's go back to x dot equal to ax. So it only depends on x, the way the behavior of the system is. Okay, good. So we'll consider this system, and we know it is autonomous LTI. Great. And it is nice to remember those terminologies because they're going to be useful, even for our course and in general, because the difference between LTI and not LTI is huge. The difference between autonomous systems and not autonomous systems is also huge. We can only discuss stability of autonomous systems, for example. Like, it does make sense to discuss stability. I mean, but okay, I will retract the statement. We can discuss stability of autonomous and non-autonomous systems, but we would have to be careful when we discussing non-autonomous systems as in terms of stability. You will see it actually in 2 lectures. Okay, good. Now let's move on. There is another question in the chat. The standard x dot equals to ax plus b also LTI, yes. So let me write it here. What the question was. First, let me clear all drawings. So the question was, is this LTI? Yes, it is LTI. It's just has a constant addition, so it is LTI. Also, you can think of B as input, or you can just see it as a constant. If you think about it as a constant, then it is autonomous system. I mean, you can think about it as an input, but if input is constant, it is still autonomous as well. So, good question. Good question. All right. So now let's dive into the math. It's going to be a little bit complicated for a second, but is extremely important. So now full attention to this slide. And yes, we'll upload the lecture recordings to YouTube, and you will have a link in the Moodle, or everything is on the GitHub. So, I would strongly suggest use GitHub instead of Moodle. I will duplicate it on Moodle as per regulation, but it's just cleaner, easier to use on GitHub. So my suggestion, just go there on our Git page, you'll find everything there. All right, so full attention to the slide now. That is that's very, very interesting and important part of the discussion. So this system, we want it to be we want to understand if it is stable or not. Now, before we do that, let us recognize. Oh, sorry. Now let us assume that we can do this type of decomposition of matrix A. What is this decomposition? It is Eigen Decomposition. What does Eigen Decomposition mean? Well, Eigen Decomposition is basically decomposition where you have two matrices V, matrix V of eigenvectors and matrix D diagonal of eigenvalues. And this is how it looks. It is possible to achieve this if you have only real eigenvalues. If eigenvalues of A, I'll write it as a lambda of A, are all real numbers, then you can do this Eigen Decomposition. So assume that you can do it. That is not true in general, but it is true for a lot of matrices. So assume you can do that. Then equation 7 becomes equation 8. Okay. All right. Now, in equation 8, what we can do is multiply both sides by V minus 1. Okay. Why can we do that? Because V inverse V is a non-degenerate matrix. How do we know that it's non-degenerate matrix? Well, because V exists. Since both of them exist simultaneously, V and V to the power minus 1, so V inverse. That means that they would have to be non-degenerate matrices. And this is true, for example. All right, so we can multiply any equation by non-degenerate matrix. It doesn't change the statement. All right, great. And here, this part of the expression becomes identity. Like this whole part, V minus 1 times V. Okay, now we can define, and here is the expression that we just wrote. Now we can define Z as V to the power minus 1 times X. It's just a definition. We define new variable. Why can we do that? Again, because V to the power minus 1 is non-degenerate. Since V inverse non-degenerate, it means we can define this new variable and we'll be able to recover X from Z by, how do we recover X from Z? Oh, like this. Oh, sorry, like this. X is equal to V times Z. Just follows from this definition and from the fact that this matrix is not changed. Okay. Now I'll try to drag this annotation bar away. Since D's are real, after we introduce this notation, what we find here is that this part is just Z dot. This part is identity, and this part is Z. So the whole expression becomes Z dot equals to D Z. And D is a diagonal matrix. So in fact, it becomes z sub I dot goes to d sub I times z sub I. D sub I here are eigenvalues because this was Eigen Decomposition, remember? So what we find is original equation 7 became a series of system of independent linear equations z dot equals to di zi. All right. So this expression downstairs, like this expression here, is actually going to be stable if and only if each individual ODE is stable, right? If at least one of those ODEs diverge, the whole system is going to diverge, right? You cannot have a partial convergence, as in like you cannot have one value diverge and another converge. I mean, it's possible, but we just call it divergence. So what I'm trying to say is, if we want this to be convergent, every single ODE has to be convergent here. Okay. And that means that for all I, the I has to be negative or 0. That would be criteria for stability. If we want asymptotic stability, then d sub I have to be strictly negative. You understand the difference, right? If one of the d sub I is equal to 0, I'll write here. If, let's say, d sub I is equal to 0, then what we have is z dot sub I is equal to 0. Hence, z sub I is equal to constant value. And it doesn't diverge, but doesn't converge either. So it is stable, but not asymptotically stable. We were talking about z here. Z converges, Z diverges. We didn't even say to which node. First of all, this system, as long as it is, as long as A is not degenerate, it only has a single node, and that single node is x equal to 0, as long as it's not degenerate. If A is degenerate, the null space of A is a node. Like every part of the null space of A is a node if it is degenerate. If it is not degenerate, then null space is trivial, and that is the whole null space. I understand that the concepts of null space are a little bit scary, but I think you did study them. We don't like you don't need to worry about that if it is slipping your mind. All I'm trying to say is every node of the system will be stable as long as this holds this or this. This is good enough for stability. This is good enough for asymptotic stability. And Y is talking about Z, gives us information about X. Well, because we know that X is just V times Z. Since, because of this definition. So if Z is stable, then X is stable, because there is a map between them. Any questions about this? This is a piece of math, extremely important, but also like substantial. So let's pause, breathe, and see if you have questions. No questions.
Will we cover Eigen Decomposition again?
You are worried that you don't understand this, right?
Probably.
Okay, let me just quickly see if I can cover it right now. It's not going to take a long time. It's hopefully it is actually pretty easy. Clear all drawings. This is one of those topics, by the way, where you would think, why would you ever try to do it without prep, right? I'm not prepared to cover it, but you know, back in my students' days, I would definitely be like, oh, that is. I cannot somehow close the chat today. What is that? Sorry about that. Just 1 second. The chat really wants to be full screen. But you know, it's actually not so scary. And that is the beauty of studying math. Eventually you'll stop being scared of those things. Just, you know, trying to motivate you to for self-study while answering your question. So eigenvalue, by definition, is something like this, right? Where this is the eigenvector, this is eigenvalue, right? Is such a vector, there is such a vector V that when multiplied by a matrix A, it scales by lambda. Okay, so we can, let's say this matrix has n independent eigenvalues. And let's say this matrix is n by n. Then you can write it kind of like this. Let me be careful here. Okay, you can write like this, right? We can define this as V, matrix V. Okay, sure. So this is matrix V. Here, what we can define it as some matrix, scaling matrix, diagonal scaling matrix with eigenvalues times the same V matrix. But we notice that I put it on the left, I can put it on the right. I don't know, like I didn't think about that. Maybe we would have to switch them around. I don't know. Let me see. Yeah, we have to switch them around. We have to put it like this. So let me just clear this. Okay. Why? Because diagonal matrices allow what do you call it? Permutation, right? You can multiply by them on the right, on the left. It doesn't matter, right? I hope I'm right. Oh, I think maybe not even. Maybe actually this is the only correct way. Maybe what I wrote initially is actually incorrect. Sorry. That's why you don't do it without prep, right? You don't want to embarrass yourself with you know, putting the diagonal matrix on the incorrect side. But anyway, doesn't matter. So what and let us define this matrix as D. So we have here this expression. And that, by the way, is often how you write eigenvalues. Like, you know, this is how you saw it in your college, like, sorry, like in your math class here, probably. Because this is slightly more human friendly. But you can also write the eigenvalues like this. Like, that's perfectly friendly as well. It's just you know, slightly more abstract. Now, imagine V is not degenerate. If there exists V1 such that so if if this matrix has inverse, or let me just write it simpler. Why do I make such a complicated statement? I can write it like this actually. If determinant of V is not equal to 0, so it's if it is not degenerate, then we can multiply both sides by V to the power -1, so V inverse on the right, and we get A equal to V d V -1. And that's Eigen Decomposition.
Can I ask something?
Thank
Yes,
you so
please.
much.
No problem. Please ask.
Yeah, in matrix V, eigenvectors are rows or columns?
Eigenvectors are columns.
Okay, thanks.
But yeah, as people pointed out in the chat, Eigen Decomposition is an algorithm. You can check out, implementations in Python. True. AV equals to VD is something that should be proven in general. So this just follows from this definition. Like, assuming that you have n eigenvectors. If you remember linear algebra, you can tell me some matrices don't have n eigenvectors, and you will be right. So not always the case. Not always the case that you have n independent eigenvectors. And definitely, so you can sometimes write, like for example, for a zero matrix like this, no matter what eigenvalues or eigenvectors you try to come up with, they're not going to be, that's not good. So maybe you'll be able to come up with independent sets of eigenvectors. I don't know. Let me not make more mistakes by giving you unprepared math. But basically what I'm trying to say is, for some matrices, they have only a single eigenvector, and you won't be able to write a not degenerate matrix here. And then this whole decomposition becomes meaningless. You couldn't do it. Also, some eigenvalues are complex. Remember, this whole argument is for real eigenvalues. So, right, hope it is good. Good enough for now. Sorry if I made any mistakes. Again, it was improvisation. Okay. Any more questions regarding what we saw on the slide? So what we let me now try to summarize what we achieved by this exercise. Oh, sorry. The summary is that for eigenvalue, for systems with real eigenvalues, the criteria of stability is that the eigenvalues are negative. Like, if matrix A has all real eigenvalues and eigen decomposition exists, then the criteria of stability is that they are all negative. That sounds very specific and not useful, and that is not the actual criteria we are going to use. But the proof that I given here is very simple, and that is the beauty. Now, maybe if I'm allowed, I will try to see if I can jump directly to the actual statement, and then we will try to prove it. Let me see, and jump directly to the actual statement. That's the thing. Yep. So as long as like the actual statement of criteria is as such, we'll go back to, let me even see if we have a slide where all this is clean. Okay, here is the criteria. So equation 17 is stable, has a stable solution. Equation 17 is stable is not very clean. You have to talk about stability of a node, not the equation. But for for linear systems, it kind of becomes the same. But anyway, equation 17 is stable. if and only if real parts of eigenvalues is extremely important detail. Real parts of eigenvalues are non-positive. And it is asymptotically stable if real parts of eigenvalues are negative. That's the actual criteria. So you take a system, find its matrix, find its eigenvalues. If they are negative, the system is stable. If they are non-negative, the system is stable. Oh, sorry, if they're non-positive, the system is stable. If you have at least one positive real part of an eigenvalue, the system is unstable. All right, but let's prove it, because we only proved it for real eigenvalues. So that's going to take a little bit of effort. So please brace yourself, but it is hopefully worth it. So let's try to do it. Okay. So consider the following system. This is a it shouldn't be bold, basically. Anyway, so consider this following system. You have two elements, x1, x2. It is just a 2x2 system. And you have this matrix. Eigenvalues of this matrix are alpha plus or minus beta, I beta. So they are complex. This matrix has complex eigenvalues. So we already cannot use our previously derived criteria. Okay. Now we start by claiming that the system will be stable if and only if dot product between this part and this part is negative. That is non-trivial. So I will first read out what we have here, and then I will draw. So please try to pay attention. It's difficult, it's not easy. But if you understand what I'm trying to say, there will be one concept late in the class, which you will understand much better. So try to pay attention. So this has to be negative. Why? Well, x dot can be, well, let me, x dot can be decomposed into two components, parallel and perpendicular to x. So perpendicular component is always 0. And what it does is changes direction. I will explain it in a second. The value parallel is responsible for the change of length. And the length would shrink only if they have opposite sign. Hence, the dot product should be negative. So if they look at the opposite directions. Let me draw now, and you will see what I mean. Okay, so imagine you have this x1, x2 space, and you know that x1 dot is equal to what was it? Alpha, I believe, x1 minus beta x2, something like this, right? To beta I didn't. I think it is something like this. Sorry, it's definitely not something like this. It is. Oh no, it is. Sorry, it is something like this. Maybe. Not important. I'm just trying to bring attention to the fact that they are related. So for any point here, you can find the value of x1 dot, x2 dot. So we can draw x1 dot or x2 dot as a vector. Let's draw it as a vector. So let's say it points this way. That is x dot. So this is x, and this is x dot. So we can have, as I said, decomposition of this vector into two components: parallel component to x and perpendicular component to x. Okay, so this component only rotates x. What do I mean the component rotates x? Well, this is still x dot, right? This is still x dot. So, you know, it's a rate of change of x. But this component only makes this whole thing rotate, doesn't change its length. This component, however, is going to change its length. And if they are collinear, so they point in the same direction, the length of x is going to increase. If, however, they are not collinear, they are like collinear as a codirectional. If they are contradirectional, the length of x is going to shrink. So if, for example, like in this case, as drawn here, the x is going to evolve kind of like this. Because you see, it's going to rotate this way and increase in size. So it's going to kind of increase like this. Now, I don't know if I have space to draw it somewhere here. Let me try to drag everything away. So imagine you have, again, the same situation here, but your x dot now points kind of like this. Okay, you know, it will be clear when I draw x. So this is x, and this is x dot. You see the dot product between them is now negative. So still it has those two components as before: perpendicular component, which only rotates x, and parallel component, which actually makes x shrink this time. Perpendicular component doesn't play any role for stability. Parallel component does. So what we want is that x times x dot for that to be negative. Okay. And if we write it out, we can say it is x dot parallel plus x dot perpendicular. But we know that x, by the definition of dot products, this is always 0. Hence, you know, this is the same as the original one. So we want this to be negative actually, but it is the same as this being negative.
We want it to be negative so the x can shrink to a point.
Yeah, so the x will shrink instead of increase. So convergence is by definition kind of like something shrinking. And the only node that we can imagine is for the original system is either 0 node or null space, node from the null space of the matrix. But we'll go towards the null space in a second. But for now, just think that 0 solution is the only solution that the system has. Any questions? Any questions about the picture? Okay. Now, with that, we achieved this criteria. Okay, we just need to now compute how it looks for this particular equation. how this criteria looks. Let's see. So let me move this way. So what we have is when we compute this guy, we basically multiply x dot here by x here. I just put the, took advantage of the fact that this is the same as this because of dot product being a scalar. So you can do the transposition. Transpose of a scalar is equal to scalar. So original scalar. Okay. Let us open the brackets here. When you open the brackets, what you find is like when you open the brackets here, you find alpha x1 plus beta, minus beta x2. And when you open the brackets here, you have beta x1 plus alpha x2. And you multiply it by x1, x2. So it becomes x1 here plus x2 here. And you see you have square here. You have a square somewhere else. Where do you have a square? Here, square here. And this is x1 times beta times x2 with a minus sign. Here's x1 times beta times x2 with a plus sign. So these components, I'm sorry for the messy drawing, but I'm just giving you a basic idea. So these components go away. I'll clean this all up. Just open these brackets for yourself and you'll see that it becomes like this. Okay. Looking at this expression 11 now, what you find is it is going to be negative if and only if alpha is less than or equal to 0. But alpha is a real part of the eigenvalue of this matrix. Eigenvalues of this matrix are alpha plus minus I beta. So we found that for this particular matrix, eigenvalue has to be negative. Okay, sounds interesting, but how much does it help? Well, at least we know now the criteria for this particular matrix. Now let's see if we can use it for a generalization, and we'll be able to use it for generalization. Here is, by the way, what we call a phase portrait. So all those small dots, small arrows are x dot, and the line is the solution. And those axes are x1, x2. And you can see how the solution looks like for a stable system. This is asymptotically stable system. If it was marginally stable or just stable, by the way, when the system is not asymptotically stable, we call it marginally stable. It's just yet another terminology. If it was marginally stable, the solutions would have looked like, sorry, I don't want to draw it. They would be like circles. We would see it next time, I think. I will have slides. Okay, good. So this is a two-dimensional case, complex eigenvalues. By the way, so I could generalize to any two-dimensional case with a single eigenvalue from here, simply by multiplying it by a transformation matrix on both sides. But let's just go directly to the general case. So general case. We'll consider this system again, and we now decompose it with Eigen Decomposition, but with complex valued eigenvalues. So this is a unitary, this is a matrix of eigenvectors. There's a matrix of eigenvalues. And we'll assume that this decomposition exists. This still does not answer the question what we are going to do if there are not sufficient number of eigenvectors, by the way. This only answers what we are going to do if there are complex eigenvectors and eigenvalues. But that is a popular scenario. So assume that you have this Eigen decomposition, but in complex, with complex valued vectors and values. Okay, same as before, we multiply both sides of this equation by u to the power -1. So I would write it here. You would have the original equation would be something like we multiply it by u to the power -1. Let me draw it in a different color so you would be able to see it better. We multiply it by u to the power -1, u inverse. This whole thing becomes identity. And we define z as u inverse x. So this becomes z dot. And this becomes z. So you have this equation here. So it's exactly the same as before, but now with complex numbers. And this is a diagonal system. However, all of those are complex. Like this is a complex number, this is a complex number, this is a complex number. This is a complex eigenvalue. Can be real, but in general case complex. This is a complex number. Why? Because by definition we multiply a real x by a complex matrix u to the power -1. So you see we got ourselves a system of independent complex valued equations. Okay, let's move on, see where this gets us. C is equal to something like this. Like any complex number can be represented in this form, and Z can be represented in this form. I would drop the J. Yeah, tutorial is in 5 minutes. Can I have a break? Yes. I'll finish the explanation. Then I'll ask Alexander to give you a break at the expense of tutorial. I know Alexander is very nice, so he will probably agree. If you want, someone can write in the chat and say that lecture is taking extra 10 minutes. So can we please start tutorial 10 minutes later? All right. So let me finish quickly here. So C is equal to this, Z is equal to this. So we can now compute their product. And their product is like, here. We can actually open it up like this. And Z dot is also can be opened up, right? And we can rewrite this whole thing as a vector. Like, what is U? U dot? U dot is alpha times U minus beta times V. So we can write it here as this equation here. What is V dot is is beta times U plus alpha times V. So this equation here. Complex numbers can be rewritten as vectors, remember. Okay, good. I mean, when you do this type of manipulation. Good. So we arrived at the exact same equation that we saw before. And this equation we already know how to solve. This equation is stable if and only if a real part of, if its eigenvalues have negative real parts. So if alpha is negative, it is stable. And what is alpha? Alpha is a real part of eigenvalue C. Hence, we know that the criteria for stability of this equation is that real parts of eigenvalues are negative or non-positive. Non-positive for marginal stability, negative for asymptotic stability. And same goes for this guy, because the eigenvalues C are actually eigenvalues of A. All right, so this was a proof. That is not, you know, not the best of the best proofs. Maybe I did some, you know, cut the corners somewhere. For example, we didn't discuss repeated eigenvalues, or the case when we don't have enough independent eigenvectors to form a basis U. That is still something to think about. But at least you get the idea of how we can get to this statement. So I will just click through the rest of the slides very quickly and we'll go to the break. So here, you saw the slide again. This is the criteria. The real parts of eigenvalues are non-positive for marginal stability. For asymptotic stability, they have to be negative. And now you know why. Okay. Here is what I promised you. This is example of asymptotic stability. You can see the solutions go towards origin. Here is stability in marginal stability. We also say Lyapunov stability sometimes. The solutions kind of have a closed loop look. So they are circles, ellipses. They go around in those orbits. That is marginal stability. And here's divergence. Why divergence? Because this solution, for example, goes away from the origin somewhere towards infinity. The solution goes towards infinity. The solution goes towards infinity. The solution goes towards infinity. So you see, this is divergence. Look here for more examples. Yeah, I will upload videos of both lectures today. Sorry, I didn't do it before. Now, here's one more example of convergence. And you can actually see which one converges and which one diverges. Like based on the arrows, you can see that this is the direction where it goes, where the solution goes. And you can see it goes towards the center. So this is a stable system. Here you can see that here's the direction where the system goes, and it goes away from the center. So this is a divergent system. Here it goes in this direction because of the arrows you can see. So it goes towards the center. But however, arrows here pointed this way. So while, oh no, I'm mistaken. Even arrows here point all this way. So this is a convergent solution. This is stable. And here you can see some arrows point this way. So this solution is going to diverge. So this is a not stable. That's basically how you can think about it graphically. Like the solution of 2x2 systems. You can just plot those arrows, find x dot for every x using this equation directly. Like, you know, this is x2, this is x1 direction, x1, and just plot the arrows and see what happens with solutions. It's easy enough. But I will leave it for you to think. The code to plot those, by the way, is with the lectures. You can find it, I think, on GitHub, together with the slides. All right, and that's it. Recommendations for this particular lecture is this one, but you'll find a lot more recommendations on GitHub. And here's where the GitHub is. So in case you want it now, just scan the QR code. Okay, that is it. Yeah, Yaroslav will have to get control of his life, and we'll take a break. Thank you, everyone, for participation. Sorry for taking slightly longer. I'll ask Alexander to give you a 10-minute break. Then you'll have a tutorial. I'll post a link to Zoom chat in the group. Thank you for coming. Bye-bye.
Hello, everybody.